So hello everyone. I will present you the Julia package InferOpt. So what is it about? So it contains state-of-the-art tools to incorporate combinatorial optimization algorithms into machine learning pipelines. And it is compatible with machine learning and autodiff ecosystem in Julia, such as Flux and ChainRules. And it is now part of the new GitHub organization, Julia Decision Focused Learning. So why do we want to use combinatorial algorithm inside machine learning pipelines? So there are two reasons. The first one is that it increases the expressivity of machine learning models by having the possibility to have combinatorial outputs, and it can also leverage algorithms for easy problems to solve harder ones. The main difficulty of including combinatorial algorithm inside the machine learning pipelines is the fact that combinatorial algorithms are piecewise constant, and we do not have informative gradients for machine learning. So InferOpt provides layers and loss functions useful for this. So let's start with a simple example. Simple application. So here we have a problem of finding a shortest path on a map. So we have an input, which is an image map, and the objective is to compute a shortest path from the top left to the bottom right corner. But the problem is that we don't know the actual costs of each cell. So we want to build a neural network that takes the image as input and predicts some costs, and then we use a shortest path algorithm, such as the Dijkstra algorithm, to compute a shortest path between the two corners. So our dataset is a set of pairs between images and paths, and we want to imitate these paths. So let's build a pipeline in a few lines. So first of all, we can use the InferOpt benchmark package to download the datasets. So here we generate a dataset with 50 samples, and so we can plot one of the samples. So we have the image, the true weights we assume we don't know, and the true path we want to imitate. And first of all, we can build okay, sorry. Like this? Is it better? Okay. So first of all, we can generate the neural network. Here we take a convolutional neural network, and we see that at the moment it's untrained, so it does not predict very useful costs. And we can also generate the combinatorial maximizer using the Dijkstra algorithm from the graph.jl library. And so we see at the moment we predict only a straight line path, but we want to output the better path from the dataset. So now that we have the pipeline, we want to build a loss function which is differentiable. So let's try to compute a Jacobian through our maximizer. And as I told you, it does not work. Here with zygotes, it fails because we have mutations in our algorithm. And if we use another package which is forwarddiff, it works, but it gives 0 everywhere because our algorithm is piecewise constant. So it's not very useful for learning. So what we do is we use InferOpt to and we use a perturb wrapper that takes as input our maximizer, and it modifies our maximizer such as it outputs now a continuous matrix, which is very close to the initial path, but it's continuous, and then it allows having informative gradients. As we see here, we can compute now the Jacobian using zygotes, and we can also define a loss function for which we have also gradients. And when we have this, we can build a full pipeline and build the training loop. As usual, here we use Flux to train, and we optimize the loss function over our training datasets. And then we can just see how we perform on the test datasets. So here we have the input image. These are the weights we predicted. So we see that he predicted high costs on the water spaces and the rock spaces, and then our maximizer just computes the right optimal path. Thank you.
We will have time for questions indeed this time. Thank you for that time. Any questions? I guess they're not prepared because I told them to ask later. But thank you for the speech.